Alright, in this video, let's talk about research designs that are non-experimental, meaning there's no manipulations of an independent variable, and there's no random assignment to groups. Another term for this would be correlational research, because it's finding a correlation, literally a co-relationship, between two or more variables, without trying to show that one of them is causing the other. So in general, we can kind of rank different types of studies by their usual level of internal validity, meaning how well they help us answer questions of causation. Like a genuine experimental design where participants are randomly assigned into groups and an independent variable is manipulated, those can potentially give really solid evidence of causation, assuming that we do it well and avoid introducing other confounds during the experiment. Then there are quasi-experiments where maybe we manipulate an independent variable, but without using random assignment. So we're actually not sure the groups start out equal at the beginning of the study. Maybe there's some other difference between them that explains the results. Or there are a sort of, quote-unquote natural experiments, meaning someone or something outside of the researchers manipulate an independent variable, so to speak, like instituting a new law in some states but not others, or instituting a new program in some schools in a district but maybe not others in the district. In this case, just like quasi-experiments, the groups, those that get the new policy and those that don't, those states that get the new law and those don't, those groups might have a lot of other pre-existing differences, like they don't start out the same. So even if one group, scores higher or acts different at the end of the quasi-experiment or natural experiment, we don't know if it's due to the independent variable or due to some pre-existing difference between the groups. So that makes for lower internal validity than with true experiments. It adds some doubts about whether our independent variable is the cause of any effects we find. So we're stuck with a lot of alternate explanations still being possible. And you can see here there's some overlap, right? Just kind of conceptually between what we might think of as like the weak experimental studies, poorly done experimental studies, and maybe really good quasi-experimental studies, something like that. But then there are correlational studies, totally non-experimental research designs where we just measure some things to see if they're related and how much they're related. So this generally tells us nothing about causation. It doesn't tell us whether A causes B or B causes A, or maybe a little bit of both, or maybe they don't actually affect each other at all, and it's some third variable, C, that is, causing them both to show up in the same way. Now, I do want to correct a misconception real quick here before we go on. A lot of people have the mistaken belief that correlational studies must only involve quantitative or numerical variables. Probably because if you've done any basic statistics, you do know there's something called Pearson's correlation or Pearson's correlation coefficient, which sure enough, you only use on numerical variables. But that's just one statistical test that happens to have the word correlation in the name. In reality, correlational studies it just means studies where the variables are only measured, not manipulated. So there's no independent variable that the experimenter is controlling or assigning people to, just variables that are measured. Those variables can be category variables like, sex or shirt color or something like that. They could be ordered category variables like, highest level of education completed, or they could be numerical variables like the ones we often think of like height or salary or score on a depression scale. Regardless of the type of variable, we can measure some variables to see if they're related, and that makes it a correlational study. So comparing the salary of dog people to cat people, that's still a correlational study, even though being a dog person or a cat person would be a categorical variable, right? It's not a numerical variable, whether you're a dog person or a cat person, but that's still part of a correlational study if all we're doing is measuring those things. Which means all the usual, basic statistical tests that you may have learned, all those that might end up, being kind of familiar for you in a course like this, those are all things that might end up being used in correlational studies. So yes, if you're measuring the relationship between two numerical variables, like weight and calories consumed, then yeah, you'll probably use Pearson's correlation coefficient, which is the R value, or something very similar, like Spearman's correlation coefficient rho, or whatever. But if you're looking at the relation between two categorical variables, like whether dog people or cat people are more likely to end up in jail, you'd use a chi-square test. This is still a correlational study, even though you're not calculating a correlation coefficient. It's still a correlational study if you're just asking people whether they're a cat person or a dog person, so you're measuring one variable, and then observing their criminal record later, so you're measuring a second variable. It's just a correlational study, but with categorical variables. And meanwhile, if you're looking at a relationship between a categorical variable and a numerical variable, that can still happen in a perfectly correlational study. And if so, you'd likely end up using something like a t-test, or maybe an ANOVA. Like if you're comparing two pre-existing groups on some number variable, that's a t-test. But if you're comparing three or more pre-existing groups on some number variable, that's a basic ANOVA, where you calculate an F value. So be careful not to assume that correlational research means you're only doing two numerical variables and calculating a Pearson's correlation coefficient R. That is a common mix-up. This is about the research design, not the specific statistics that we use. Okay, but for now, let's move on. Let's think about why anyone would bother doing these correlational studies, these totally non-experimental studies, when that kind of study, it sucks for answering causation questions. Well, in some cases, we use those studies because we just don't care about causation for those purposes. Maybe simply prediction is enough in those cases, in which case, who needs to worry about pesky internal validity stuff? So for example, insurance companies don't give a crap if being young and being male causes more accidents. They just know those things are correlated, and that's enough for them to set their pricing tables for insurance premiums and make sure they make a profit. Likewise, big data algorithms may not care why some characteristics or behaviors are correlated. They just care that those things are predictably related. Likewise, if you want to know whether, verbal intelligence and mathematical intelligence are related, you might not be worried about whether there's a causal connection between them. You might just want to know if people who are good in one of those realms will tend to be good in the other. Also, sometimes, we do care about causation, but before investing in an expensive experimental research study, we just want to collect some exploratory data. Just kind of explore a topic first to get the lay of the land. It's much cheaper and easier. So you'll see studies all the time where, we likely do care about the causal direction here, but we first want to establish that there's some sort of relationship. Then we can invest the money. We can try and confirm if our intuitions are correct about, what's causing what in these cases. Other times, we can only do correlational research designs for ethical reasons. Like sometimes we can't manipulate the independent variable because doing so would be horrible. For example, if you think there's a link between smoking and pregnancy and the child having some condition later on, we don't want to do an experiment where we randomly assign half of pregnant mothers to smoke a bunch. Likewise, if we think some disease is causing a particular symptom, we want to test that out, see if it's actually the case. We don't necessarily want to do an experiment where we randomly assign half of our participants to get infected with the disease just to see if they develop that symptom. So basically, we've got plenty of reason to still do correlational research, especially since it's usually much easier and much cheaper, which also means we can usually get a much larger sample size. It's much easier to get a representative sample, of the whole population. There are benefits, and sometimes it's our only option. And while I try to repeat over and over that correlation does not imply causation, that correlational research, it can't fully answer questions whether A causes B or not. I should add there are some forms of correlational research that at least can offer us a bit more internal validity than others, right? So a little further to the right on this scale. Basically, even if they're correlation on the left, they can be better evidence than other correlational studies. So just for a very simplified example, imagine we're studying the so-called beer goggle effect, which is the claim that the more you drink alcohol, the more attractive other people seem. So imagine we do a purely correlational study where we go to a bar at night, we ask people how many drinks they've had, and then we ask them to rate a picture of some stranger for how attractive they find that person. Or maybe a bunch of pictures, whatever. It's not an experiment. Like, we did not assign some people to drink 2 beers or 6 beers. We just measured both variables. So this is purely correlational research. Even if we did this in a laboratory and just asked people to come from the bar over to our laboratory to do it, if we didn't assign the level of alcohol to them, it's not an experiment, just measured. So our data might look like this. More beers that you've had, more attractive, all for the same picture you're looking at. On the other hand, though, maybe we do the same study, but our data looks different. Maybe it looks like this. In that case, there's not so much of a clear pattern of more beer equals more attractiveness. So this data would be much less convincing if you're trying to argue for the beer goggle effect from this correlational data, even if we get some, statistically significant correlation there. So in correlational data, we can look for something like what's often called a dose-dependent response, meaning that there's not just a correlation between, say, smoking and lung cancer, but those who smoke the most have the highest rates of lung cancer, and those who smoke a medium amount have more medium or moderate rates of lung cancer, and those who smoke a small amount don't have nearly as increased a rate of lung cancer. This kind of thing, it still does not establish causation by any means. It's not an experiment, since we can still easily explain those results in other ways. But if there was not a dose-dependent response, right, if we got results like this, then causation would be unlikely. So this is kind of an extra double check of the correlation being in a particular pattern that might make us a little more confident it's at least worth doing experimental tests for causation afterward. So, okay, how is correlational research done? It can be any method at all where you are just measuring variables and not manipulating them. So doing a study in a carefully controlled laboratory setting, that does not mean you're doing an experiment. We're very precise about using the word experiment when we're talking about research designs. If all you do is measure variables in your laboratory, it's still a correlational study. Like, bring people into a sleep laboratory and say you measure their REM sleep that night, and then you also in the morning measure their VO2 max, during vigorous exercise on a laboratory treadmill. That's correlational. You measured sleep, you measured, lung capacity or oxygen, but that's just correlational, even if it's all done in a lab with fancy equipment. But of course, you'll also usually see things like surveys, right? That's maybe the most common way to do correlational research. Ask a bunch of self-report questions and see which answers correlate with which other answers. Or give a questionnaire about, someone's eating patterns, and then give a different questionnaire, maybe like a psychometrically validated scale that measures depression, and you can see if eating patterns relate to depression. That's correlational, right? There's no experiment there. Then there are some other setups like naturalistic observation or doing research on archival data, things like that. So let's talk about a couple of those in a little more detail. Naturalistic observation is just a type of correlational research where, again, we're just measuring variables. In this case, kind of purely observing and describing things from a distance, maybe. So no manipulating variables, no assigning people into groups. We just kind of look at what's going on out there in the world. Now, we might be comparing pre-existing groups, like we might be seeing as we watch out in the wild if license plates from a particular county correlate with the behavior of drivers at stoplights. But we don't assign people into those groups. We just kind of sit there with a metaphorical clipboard or maybe a literal clipboard and tally up those behaviors, tally up those characteristics, and see if they're statistically related, see if they're correlated. Now, one benefit of naturalistic observation is that it's generally unobtrusive, so you get to see behavior out in a realistic setting, which might be better than testing people in a laboratory sometimes, where they might act different when they know that they're being studied. But since it's just correlational and can't answer causation questions, this is one of those methods that's probably best when you're kind of clueless about a process or behavior and you just want to kind of watch for a while and get an idea of the basics before you do further research that might be harder, more invasive, more intrusive, more expensive, things like that. Now, some very simple examples might be sitting on the quad on campus, counting how many people use their phone while they're walking, or comparing the percentage of men versus women who hold doors open for others, or maybe even observing the timing of how long people wash their hands when they think they're alone in the bathroom. Now, one downside of naturalistic observation is that there's often a bit of a subjective component. Some sort of researcher judgment is involved in describing or in quantifying the behaviors that you're watching. Now, it won't fix everything, but the most common solution to this is to have 2 or more independent observers. Or maybe you take video when you're doing it and then have 2 or more people independently coding those same videotapes. So independently coming to the conclusion of whether they'll count this particular thing as an instance of the behavior you're looking for. Then you can statistically check for inter-rater reliability. So reliability between the raters, so correlation between their ratings, to make sure their scores, go together in the same circumstances. In other words, make sure they both count the same behaviors in the same way. So that can fix a lot of problems with naturalistic observation. Now, another common type of correlational research is not to go out and collect any new data per se, but to find some existing data source and then look for correlations, so relationships, between things in that have been measured or quantified already. So for example, maybe you have a hypothesis that sports participation is correlated with good grades. Instead of measuring current students who are athletes or non-athletes, you might just go look at old school records that already exist. You can get a much larger sample size, right? If you can go just find school records everywhere and maybe see if sports participation was correlated with people's grades. Maybe you even compare if that relationship was different in the 50s versus the 80s versus the 2010s to see if the relationship holds or changes over time. That would be archival research. But again, it doesn't tell us if playing sports makes your grades better, nor does it tell us if getting good grades makes you more likely to sign up for sports, or if some third variable connects them, like, socioeconomic status or something, where people in the most well-off families, they've got resources to play sports and resources to get extra school tutors. Maybe those in poorer families have to work a lot, so their grades slip, and also it precludes them from sports that take a bunch of time. Like, there's always other explanations with correlational data, and that's going to be the case with archival research. Now, another example might be, finding a bunch of people who've already developed and been diagnosed with schizophrenia, and you check into their past records to see what past life experiences might correlate with the diagnosis. Like, did those people have a higher rate of adverse life events or chronic stressors compared to the general population? That's something you can answer with archival data, and it may help you spot an interesting pattern that connects the two variables, but again, it doesn't mean for sure that one causes the other. Or there was a kind of a funny study in 2009 looking into what predicts marriage success, where they actually just looked at people's old photos, and they found that smiles or frowns in those past photos predicted whether a couple ended up divorced or not. So like the most smiley people in the study didn't really get divorced, but the least smiley people had a higher divorce rate. That's archival research. It's going back, in this case, looking at old photos and comparing to, marriage and divorce records. But again, it's correlational because we have no evidence that the smiling behavior had any effect at all on the marriages. We haven't done an experiment yet where we manipulate smiling. We make some people smile or train some people to smile and some people to not smile. That would be an experimental design which would help answer causal questions. At any rate, things like archival research and naturalistic observation, they are just some forms, some other forms are out there of correlational research that go along with the usual stuff like surveys and questionnaires or, just measuring multiple things in a laboratory without manipulating any independent variable. Now, I do want to mention before we go on, there are more complex versions of correlation, both in the design and kind of in how you handle it statistically, that may try to improve our internal validity by ruling out some plausible alternative explanations. So you can't rule out all alternative explanations with a correlational study. You could never do that, but you could at least rule out some by checking for them. So you won't ever be sure that one variable caused the other, but maybe you can be a little more confident since you ruled out the most obvious alternative explanations for whatever observed correlation you found. So for example, there's a technique called multiple regression that lets you detect how much the correlation between A and B still sort of exists once you factor out the effect of other potential third variables like age, socioeconomic status, gender, or whatever you choose to measure and check. You can kind of statistically control for these variables, so to speak, in essence sort of see if A and B are still related when you hold these other things like age and gender constant. Now, as I've said before, some correlational research designs are stronger than others when it comes to internal validity, even if they'll never be as good as a well-designed experiment. So this is how, modern epidemiological research is often done. We can't be sure, for example, that red meat is causing heart disease, but we can rule out a lot of other third variable explanations when we find a correlation between those two things. Like we can measure exercise level, gender, age, alcohol use, smoking, whatever, and see if the correlation between red meat and heart disease still exists once we control for those things or hold them steady statistically. And if that relationship still exists, then we can be a little more confident in the plausibility that one of those variables, red meat, might be causing the other, heart disease. Now, there might be other things we hadn't thought to measure and control and rule out that would explain it. So again, it's not proof. Now, finally, I just want to end with a little example to demonstrate an important point. For any given research topic, it can often be studied in multiple different ways, and we may need to do a lot of research across many different types of studies before we start having a solid idea about that topic. But also, you may see some people doing studies and publishing things where the study is done with a pretty crappy research design, and we should not take it very seriously, or we should say, okay, this is at most reason to do some real, good studies later. So, okay, let's just walk through this example here. We're going to talk about a real world worry that some people have had. You might hear people make claims on TikTok or Instagram that they think cell phones might cause brain cancer. So, they say you shouldn't hold your phone to your head when you talk, something like that. Now, is that true? Like, how would we actually answer something like that scientifically? I mean, you've probably seen studies in the news that do try to answer that question. Like this news article in 2011 describing a study by that was published in the British Medical Journal looking at 350,000 people where they found absolutely no correlation between phone use and cancer. But how did they collect that data? How did they measure those variables? And how might we study this kind of question if we were starting from scratch? So you might pause the video and brainstorm a couple ways of studying a topic like this. Well, let's start with just a made-up, hypothetical, kind of silly example. Imagine that a researcher is sitting around one day and reads some report that Egypt happens to have a lower rate of brain cancer than the United States. Wow, Egyptians just get brain cancer less. Maybe this researcher thinks, oh, that could provide a good test for this whole phone cancer link thing. So he goes and he spends 2 weeks in Egypt watching people in a busy park, and he records how much time each person spends talking on a cell phone or not talking on a cell phone. Then he returns to the United States and he repeats those same kind of observations for 2 weeks in a busy park here in the United States. He might hypothesize that he'll see Americans with their phones to their ears much more often than Egyptians. If so, if that's what he actually finds, maybe that would be why Americans have more brain cancer. Now again, this is all made up for a hypothetical example here. I don't know the rates of brain cancer in these countries. But okay, so what kind of research design has he done here? Maybe pause and try and name the research design. Well, he's not manipulating how much people use their phones, so it's not an experiment. This is a correlational study. And specifically, he's doing naturalistic observation of their phone using behavior, right? He's just out there in the wild, tallying things up, probably without people realizing they're even in a study. Meanwhile, for the cancer rates, maybe it sounds like that'd be archival data, right? But in any case, this is correlational research. It's non-experimental. So if he does find that Egyptians put their phones to their heads less, Americans have their phones to their ear more, and that Egyptians have lower rates of brain cancer, Americans have higher rates, would we conclude that cell phones cause cancer? Is this good evidence for that? And I would say, God, no, because he didn't do an experiment. Maybe there's a third variable. Maybe something else in Egypt, like, I don't know, dietary differences, or even a genetic propensity, or maybe pollution levels are different in the countries, or maybe there's some cultural practice that kind of affects cancer rates, something else they do that exposes them to something that changes cancer rates. Maybe that's behind the difference in those cancer rates, and it has nothing to do with cell phones. Third variables are always possible with correlational research. Okay, how about this research on the topic? Again, I'm totally making this up for an example, but just imagine there's some doctor that you read about this in the newspaper or something. Some doctor, they write up a report, that her 26-year-old patient has a brain tumor on his right temporal lobe, which is right next to his right ear. So in an interview, the patient, when talking to that doctor, maybe the patient says he spends more than 6 hours a day on his cell phone for work, and he always, holds it next to his right ear. Maybe the doctor also remembers that one time she had a similar patient, it was a while back, that had some rare brain tumor at a kind of young age on the right side of her head, and she also used her phone a lot. So the doctor, maybe she publishes an op-ed in the newspaper decrying the danger of cell phones and telling parents to limit exposure for children. Comes from a good place, right? So the question is, do we have good evidence, right? We've got another non-experimental research design here because there's no independent variable being manipulated and no one randomly assigned into groups. So should this convince us that cell phones cause cancer? When you read this op-ed, it might sound kind of like intuitively convincing, but no, because all we've got here are two anecdotes. And let me tell you, the plural of anecdote is not data. Now, there's a good chance here it could just be coincidence. Like someone could run into two cases like this during their career, and a bunch of other doctors out there probably don't run into those exact same cases, but the person just happens to notice and think and like kind of note a pattern or something. They think there's a pattern there. So maybe because of some preconceived notion that doctor had, the doctor just happened to notice these two patients, and as a part of sort of confirmation bias, maybe she forgot about the many other brain tumor patients that she's seen who are light phone users or didn't use their phones at all, or had tumors in other positions nowhere near where they use their phone, or maybe heavy phone users who had no health problems at all. Like, there are no newspaper articles being, bothered to be written up for the hundreds of other times that someone gets brain cancer but isn't a heavy phone user, or gets cancer in other parts of their body. There are no newspaper articles for the millions and millions and millions of people who use their phones just as heavily but have no cancer, or have cancer in a different part of the body or whatever. So a totally non-experimental case study like this would not provide any solid evidence that phones cause cancer. Okay, so how about this research idea? Let's say we recruit 1,000 people, we get their consent, and then we randomly assign 500 of them to not use any cell phone for 5 years, or maybe just to never put it to their head during phone calls, whatever our design is. And then we randomly assign the other 500 to use their phone as often as they want. Maybe we even give them a free phone with free minutes, unlimited. We pay for their bill so they can call as much as they want. Then 5 years later, maybe you measure brain cancer rates in each of those groups and compare the two groups. So first off, what kind of research design is this? Well, it's a true experiment, right? We manipulated an independent variable, so that would be their phone use, and we measured a dependent variable as the outcome. So if hypothetically the use group is higher in cancer than the not use group, do cell phones cause cancer? Now here, we've moved beyond correlation to an experimental design, and those are the kinds of things that can help us answer causation questions. And the groups here, we used random assignment, so the groups started out equal in pretty much every way. So in this made up example, again, this is all made up, I'm not saying these are real results, it feels like if we found this pattern, that would be pretty strong evidence, right? It's experimental. Except, can you think of any confound that might be introduced during the study that might make the cancer rates different for reasons other than phone use? Well, for one thing, we haven't actually established that the use group actually did use their phones more. We didn't watch or measure their actual phone use behavior in any way. So we don't know that those groups actually used their phones a different amount. But also, if we gave a free phone to the use group, to encourage them to call a lot, maybe that also freed up some of their monthly income. So now they no longer have a phone bill to pay, they've got extra money, and that might make them more likely to buy McDonald's a few extra times a month. And it's actually the diet change that affected their cancer rates. Yeah, it's kind of a silly example, right? But it's meant to show that even in an experimental design, that's not always necessarily conclusive. A single study alone will never be conclusive, and we can often think of some other confounds that might show up even in an experiment. For that matter, 1,000 participants, it might sound like a lot, like that's a pretty good sample size for a lot of things, but when you're dealing with a rare occurrence, like an uncommon type of cancer where the base rate is low, we may be comparing a rate of, our results might be 2 cancers in one of the groups and 4 cancers in the other. That's not a ton of data to make a sweeping conclusion from. All right, how about this then? Let's say we go with a much larger sample size. Maybe we recruit 80,000 volunteers for a huge study. Maybe it's sponsored by the government. So we get consent to have access to their cell phone records directly from the phone company, so you can actually tally up their phone usage. That was something we had missing before, right? We weren't actually measuring the phone usage. Now we can get a decent measurement of their phone usage, at least the average minutes per day for each person. Now let's say we follow those 80,000 people longitudinally for 10 years. We track their phone use for 10 years, but we also send them an occasional survey at regular intervals, just asking, have you been diagnosed with brain cancer, yes or no? This would let you record something like how many years have passed without them getting cancer, so we can see if the number of minutes per day that they spend on the phone is related to the number of years that they go without cancer. So first off, what kind of research design is this? Pause and think about it. Well, it's just measuring two variables. It's not manipulating an independent variable, so this is correlational research. And if we did happen to find a correlation here, again, this is made up data, but if we did find a correlation here, would that be good evidence? Would you conclude that cell phones cause cancer? Well, as with all correlational research, there are alternative explanations, including some you may not have thought of. Maybe someone else could think of some. Like, I don't know, maybe people who could afford unlimited minutes, meaning people who make good money, tend to eat more steak than people who can't afford unlimited minutes. Maybe it's steak that increases cancer risk, not phone use, or, something else that people with a lot of money do that people with a lot of money, don't do. Or maybe people who just have a propensity to talk on their phone rather than texting, people who prefer voice conversations to texting, those mutants, do they differ in other ways? Maybe they tend to smoke more than people who prefer texting, and it's actually the smoking that causes cancer. Or maybe there's some other difference in the type of people who, for some reason, prefer to talk on their phone a lot to the people who don't. It might be that other difference between those pre-existing groups that is behind any cancer rate differences we find, meaning it's not the phone usage at all. That's why even if we find a correlation, the correlation is never very convincing. We might not even realize what the third variable possibilities are, but I'm guaranteeing you they're always there, an unlimited number of possible alternative explanations for our data that we haven't yet ruled out. So there's yet another way we could maybe research this question, and that would be doing an animal study, so studying an animal model. Like, imagine we take 75 rats, all the same breed, the same age, the same housing. So this is a really good controlled lab setting. We've ruled out a lot of differences. We know that these are, the same basic rats and everything. We put maybe an identical model of a cell phone in each rat's cage. So it's the same exposure to cell signals. In this case, we're going to use random assignments. Maybe we randomly assign a third of them to be in a cage with a non-functional phone. So it's turned off and has the antenna removed, no cell signal. We randomly assign 25 to have a normal functioning phone that's turned on and has good signal strength, and another 25 to be, live around this turned on phone, but with poor signal strength. Because sometimes, maybe they boost the signal more when they're trying to find a cell tower nearby. Whatever it is we think might make a difference here. So let's say we do this, we set it up, and then 3 months later, which is a pretty long time in a rat lifespan, by the way, we measure cancer rates at each group, and we compare the three groups' cancer rates. So first off, what type of study is this? How do we describe it? Well, this would definitely count as an experiment since we did random assignment of groups and thus we manipulated an independent variable, the cell signal exposure. And the question is, if we saw something like higher cancer rate in the poor signal group, maybe compared to the good signal group, and they had even higher a higher cancer rate than the off group, would you conclude that cell phones cause cancer? Well, it is an experimental design, so it should be able to, directly answer questions of causation. Let's say if this was replicated in a bunch more rats, I don't know, to me this feels like pretty strong evidence there may be a real effect here. We could possibly think of some other confounds we want to test and rule out. But even if we get pretty confident about this experimental design, we've still only demonstrated the effect for rats. We've only demonstrated causation for rats. Maybe humans are different. Our bodies have like 200 times the mass of a rat and very different metabolism. So maybe the very minor levels of non-ionizing radiation that comes out, maybe those affect them, but not us. Meaning even if we have solid evidence of phones causing cancer in rats, we can't be sure they're an issue for humans. But again, these examples have all been talking about totally made up hypothetical results. None of this is real. The point is, it's not about cell phones, I'm talking about this stuff, but about the challenge of answering complex questions and the variety of research designs that we might use or be tempted to use or see other people use when they try to answer such questions. So you'll see this in all sorts of research, like people trying to study internet addiction or something like that. And you might look and be like, oh, in this study, they didn't manipulate people's internet use behavior at all. They just measured things. Hopefully you're starting to see how some forms of evidence are much stronger than others. And it's not just a matter of sample size. That hypothetical study I made up of 80,000 people, that was a purely correlational research design, which again, isn't great at convincing us that one thing causes another. Often, the fundamental research design, the type of study, is much more important than having a giant sample size. Yeah, you can get big sample sizes cheap with correlational research, but often the experimental design is what you want and a smaller sample size is fine. It's still strong enough. But even then, one well-designed study, even using an experimental design, is still often going to leave open a few possible confounds, a few alternative explanations. Not to mention, there's always some small chance the results were just a statistical fluke, which is why it often takes a lot of studies to start to form a firm conclusion about how things work out there in the world.